Hey, welcome back to Stardrift FM. It's late. The kind of late where the world gets quiet and your thoughts get loud. Perfect time for what we're about to do. Tonight, we're going deep, really deep. We're talking about one of the biggest questions humanity has ever asked. And I'm going to try to convince you of something that might change how you see the night sky forever. But first, take a breath. Get comfortable. Maybe you're lying in bed. Maybe you're driving somewhere. Maybe you're just existing like the rest of us, trying to figure out what all this means. Here's the question: where is everybody? I mean, think about it. The universe is incomprehensibly big. Like, your brain literally cannot process how big it is. Billions of galaxies, each galaxy with hundreds of billions of stars. Many of those stars with planets. Some of those planets probably a lot like Earth. The universe is also incredibly old, 13.8 billion years old. That's enough time for life to emerge, evolve, build civilizations, colonize galaxies, and do it all over again, thousands of times. So where are they? Where are the aliens? This question has haunted scientists, philosophers, and late-night thinkers like us for decades. It's called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a lunch conversation back in 1950. And tonight, I want to explore one possible answer. An answer that's both humbling and kind of terrifying. An answer that suggests we might be more special than we ever imagined. What if we're early? What if the reason the universe is so quiet is because we're among the first to show up? Let's find out. Okay, let's back up a bit. Before we can talk about solutions, we need to really understand the problem. The Fermi paradox isn't just, hey, where are the aliens? It's a mathematical contradiction. The numbers say intelligent life should be everywhere. But when we look, nothing. Silence. Just us, staring at the stars, waiting for a signal that never comes. Let me walk you through the math. Then don't worry, I'll keep it simple. We're all tired here. Our galaxy, the Milky Way, has somewhere between 100 and 400 billion stars. Let's be conservative and say 200 billion. That's 200,000 stars. Just in our galaxy. Now, recent discoveries have shown that most stars have planets. Not some stars, most. So let's say at least half of those stars have planetary systems. That's 100 billion planetary systems in the Milky Way alone. How many of those might have Earth-like planets? Planets in the habitable zone, with liquid water, rocky surface, the good stuff? Estimates vary, but even conservative ones suggest at least 1% might be potentially habitable. That's still 1 billion Earth-like planets in our galaxy alone. And remember, there are at least 200 billion galaxies in the observable universe, maybe more, maybe 2 trillion. We keep finding more every time we build better telescopes. So we're talking about, I don't know, something like 1 billion trillion potentially habitable planets in the observable universe? The number is so big it stops meaning anything. It's just a lot, a whole lot. Now here's where it gets interesting. Our universe is 13.8 billion years old. Earth is about 4.5 billion years old. Life on Earth appeared pretty quickly, maybe within the first billion years. And then it took about 4 billion years to go from simple cells to us, podcasts, smartphones, existential dread. But here's the thing. Even if intelligent life is incredibly rare, even if only 1 in a billion habitable planets develops intelligent life, that's still millions of civilizations in our galaxy alone. And many of those stars are older than our sun, some by billions of years. Which means if life emerged on planets around those stars at the same rate it emerged on Earth, those civilizations have had billions of years head start on us. Billions of years. Think about that. Humanity went from cave paintings to landing on the moon in about 50,000 years. From the first radio transmission to smartphones in about 100 years, technology advances exponentially. Now imagine a civilization that's 1,000,000 years ahead of us, or 100 million, or 1 billion. They should have colonized the entire galaxy by now, multiple times over. Even at slow speeds, even being careful, even taking their time. A civilization with a billion-year head start should have spread across every star system in the Milky Way. They should have built megastructures we could see. They should be harvesting the energy of entire stars. They should have sent probes to every corner of the galaxy, including here. But when we look up, nothing. No signals. No megastructures, no probes, no visitors. Just stars twinkling silently, keeping their secrets. That's the Fermi paradox. The math says they should be there. Reality says they're not. Something doesn't add up. For 70 years, scientists have proposed dozens of explanations. Maybe aliens are hiding. Maybe they destroyed themselves. Maybe we're in a simulation. Maybe they're so different we can't recognize them. Maybe they're already here and we don't know it. But tonight, we're focusing on one explanation. One that I find both the most scientifically supported and the most emotionally resonant. We're early. So what does "we're early" actually mean? It means the reason we don't see aliens isn't because they're hiding or dead or too weird to communicate with. It's because they don't exist yet. Most of them haven't been born. The universe is still young, and we're among the first conscious beings to open our eyes and look around. I know, the universe is 13.8 billion years old. That sounds ancient. How can that be young? Well, young is relative, and when you zoom out to cosmic timescales, 13.8 billion years is actually not that much. Let me explain. Stars will keep forming for trillions of years. Not billions, trillions. The last stars won't burn out for something like 100 trillion years. That means we're currently living in the first 0.01% of the universe's stellar era. We're not in the middle. We're not at the end. We're right at the beginning. Think of the universe like a party. The party is scheduled to last 100 hours. We showed up in the first 6 minutes, and we're looking around wondering why the room is empty. That's what's happening. The universe is 13.8 billion years old, but it's going to be doing interesting stuff for trillions more years. We're early, cosmically, absurdly, almost comically early. But there's more to it than just timing, because you might say, sure, the universe will last a long time, but 13.8 billion years is still plenty of time for life to emerge, right? Well, maybe not. Here's where it gets really interesting, because it turns out the conditions for life as we know it might not have been possible for most of the universe's history, and that changes everything. Let's talk about what you're made of. Look at your hand. That hand contains carbon, oxygen, nitrogen, calcium, iron. Your blood has iron in it. Your bones have calcium. Your DNA is built on a backbone of carbon and phosphorus. Now here's the thing. None of those elements existed in the early universe. When the universe began, there was only hydrogen and helium. That's it. The two simplest elements. Just protons and neutrons hanging out, forming the most basic atoms possible. Carbon didn't exist. Oxygen, nope. Iron, not a trace. Nothing heavier than helium existed anywhere in the entire universe for a long, long time. So where did all those heavier elements come from? Stars. They came from stars. See, stars are basically giant fusion reactors. They smash hydrogen atoms together to make helium. Then they smash helium together to make carbon. Then carbon to make oxygen, and so on up the periodic table. But there's a catch. A star can only fuse elements up to iron. After iron, fusion starts costing energy instead of releasing it, so iron is where stellar fusion stops. But wait, you might say, there are elements heavier than iron. Where do those come from? Supernovae. When massive stars die, they explode. And in that explosion, in that catastrophic moment of destruction, The energy is so intense that heavier elements get forged. Gold, silver, uranium, all created in the death throes of giant stars. And here's the key point. All of these elements then get scattered across space, mixing with gas clouds, eventually becoming part of new stars and new planets. So the first generation of stars, they had no heavy elements. They couldn't have had rocky planets like Earth. No carbon-based life, no liquid water, nothing we would recognize as habitable. It took time for stars to live, die, explode, scatter their guts across the cosmos, and seed the next generation of stars with the elements needed for planets and life. How much time? A lot. Billions of years. The first generation of stars formed maybe 200 million years after the Big Bang. They were massive, burned bright, and died quickly in just a few million years. They exploded, seeding space with the first batch of heavy elements. Then the second generation of stars formed. Some of these could have had rocky planets, but the concentration of heavy elements was still low. Maybe some had planets, but probably not many, and probably not very Earth-like. It took multiple generations of stars living and dying over and over, slowly enriching the universe with heavier elements, before conditions were right for planets like Earth to form. Our Sun is what astronomers call a population I-star. It's relatively rich in heavy elements. It formed about 4.6 billion years ago from a cloud of gas that had been enriched by multiple generations of previous stars. Earth, in other words, couldn't have existed in the early universe. The ingredients weren't there yet. And if Earth couldn't have existed, neither could life like us. Some scientists estimate that Earth-like planets probably couldn't have formed until maybe 8 billion years after the Big Bang. Others put the number even later. But the point is, for a significant chunk of the universe's history, life as we know it was chemically impossible. The universe had to cook for billions of years before the recipe was ready. Okay, so the universe needed billions of years just to make the ingredients for life. But once you have the ingredients, how long does it take to actually make life? An intelligent life? Let's look at the only example we have, Earth. Earth formed about 4.5 billion years ago, and the earliest evidence of life dates back to maybe 3.8 billion years ago, possibly even earlier. So life appeared relatively quickly, maybe within the first 500 to 800 million years. That sounds fast. That sounds like life is easy, like it just pops up wherever conditions allow. But here's the catch. For the next 3 billion years, almost nothing happened. I mean, life was there. Single-celled organisms floating around in the ocean, bacteria and archaea doing their thing. But for 3 billion years, that was it. No animals, no plants, no brains, just microbes. Think about that. For most of Earth's history, the most complex life form was basically pond scum. Complex multicellular life didn't appear until about 600 million years ago. That's the Cambrian explosion, when suddenly, boom, eyes, limbs, shells, predators and prey. Evolution went nuts. But even then, it took another 600 million years to get to humans. Dinosaurs ruled for 165 million years and never developed technology. Intelligence like ours is not guaranteed. It's not inevitable. It might be incredibly rare. Let me put it another way. If you compressed Earth's 4.5 billion year history into a single 24-hour day, life appears around 4 a.m. Complex multicellular life doesn't show up until around 9 p.m. Dinosaurs appear at 10:40 p.m. and go extinct at 11:40 p.m. Humans show up at 11:59 and 56 seconds p.m. All of recorded human history happens in the last fraction of a second before midnight. We are a blip, a cosmic afterthought. The universe spent most of its time on Earth just waiting, running the same simple program for billions of years before anything interesting happened. And this might be normal. This might be how long it takes everywhere. There's a concept in astrobiology called hard steps. The idea is that the evolution of intelligent life requires passing through several extremely difficult transitions. Steps that are so hard, so unlikely that each one takes billions of years of waiting for a random chance to succeed. What might these hard steps be? The origin of life itself, going from chemistry to biology. We still don't know how this happened and might be incredibly unlikely. The evolution of complex cells. Our cells have nuclei, mitochondria, specialized structures. Early life didn't have these. The jump from simple bacteria to complex cells was huge and might have been extremely improbable. The evolution of multicellular life. Getting cells to cooperate, specialize, form bodies. This took billions of years to happen on Earth. The evolution of intelligence. Most complex life never develops human-level intelligence. Dinosaurs were around for 165 million years and never built a radio telescope. Each of these steps might be a massive filter, an unlikely leap that takes enormous amounts of time. And if each step takes an average of 1 billion years, then you need a planet that remains habitable and stable for billions of years just to have a chance. The Earth has been habitable for about 4 billion years and we only just made it. A planet that had been habitable for only 3 billion years might never have reached the intelligence stage. The window might be too short. This suggests that intelligent life isn't just rare, it's slow. It takes billions of years to cook. And if that's true, then even with a 13.8 billion-year-old universe, there might not have been enough time for many civilizations to emerge yet. We might be among the first to make it. All right, let's put some numbers to this, and I promise I'll keep it simple. There's a fascinating paper by Robin Hanson, Daniel Martin, Calvin McCarter, and Jonathan Paulson called "If Loud Aliens Explain Human Earliness, Quiet Aliens Are Also Rare." Big title, big ideas. Their basic argument goes like this. If intelligent civilizations were common and long-lasting, and if they tended to expand across the galaxy, we should see evidence of them. We should see them everywhere. The galaxy should be colonized by now, but we don't see them. The galaxy appears empty. Now, there are two ways to explain this. One, intelligent life is incredibly rare. So rare that we might be alone in the galaxy, or even the observable universe. The filters are so hard that almost no one makes it through. Two, intelligent life isn't that rare, but we happen to be very early. We're among the first. Others will come, but they haven't emerged yet. The Hansen paper argues that option 2 is actually quite plausible. They calculate that if life takes a long time to emerge, which the evidence suggests it does, then we might be living in the first few percent of all civilizations that will ever exist. Let me say that again. If their math is right, we might be in the first few percent of all intelligent beings who will ever live in the observable universe. That's not a small claim. That's a profound claim about our place in cosmic history. Here's another way to think about it. The universe will keep making stars for trillions of years. Most stars that will ever exist haven't been born yet. Most planets that will ever exist haven't formed yet. Most potential habitats for life are still in the future. If intelligent life takes billions of years to emerge, and if the universe is only 13.8 billion years old, and if habitability requires certain chemical conditions that only became common in the last several billion years, then we're not late to the party. We're not even on time. We're ridiculously, cosmically early. The party hasn't started yet, and we're standing in an empty room, wondering if anyone else is coming. Now, I've been making the case for we're early, but I want to be fair. I want to present the other side. Because science isn't about convincing people of what you believe. It's about honestly examining the evidence and acknowledging uncertainty. So let's talk about the problems with the "we're early" hypothesis. First problem, the Copernican principle. For the last 500 years, science has repeatedly shown that we're not special. Earth isn't the center of the universe. The sun isn't special. Our galaxy isn't special. Every time we thought we were unique, we turned out to be ordinary. Their "we're early" hypothesis seems to violate this principle. It says we are special. We're among the first. We're rare. Some scientists are deeply uncomfortable with this. They argue that any theory that makes humans special should be treated with suspicion. We've been wrong about being special too many times before. That's a fair point, but here's the counter-argument. The Copernican principle says we shouldn't assume we're special without evidence. It doesn't say we can't be special if the evidence supports it. If the evidence genuinely points to us being early, then that's what the evidence shows. We shouldn't reject it just because it feels too flattering. Second problem, maybe life is faster elsewhere. We're basing our estimates on Earth's timeline. Life took 4 billion years to produce intelligence here. But maybe that's slow. Maybe on some planets conditions are better. Maybe evolution runs faster. Maybe intelligence emerges in 1 billion years instead of 4 billion. If that's the case, then there's been plenty of time for other civilizations to emerge, even with the constraints we've discussed. This is a legitimate uncertainty. We have exactly one data point, Earth. We don't know if Earth is typical or unusual. Maybe we're slow. Maybe we had bad luck. Maybe other planets speedrun the evolution game. Third problem, maybe they are out there and we just can't see them. The "we're early" hypothesis assumes the universe looks empty because it is empty. But maybe it's not. Maybe aliens are out there and we're just not looking right. Maybe they communicate in ways we can't detect. Maybe they're avoiding us deliberately. Maybe they're so advanced they're invisible to our primitive instruments. This is the zoo hypothesis, or dark forest type thinking. And it's possible. We can't rule it out. But here's my counter. Each of these alternatives requires additional assumptions. They require aliens to exist and to be hiding, or to be undetectable, or to be avoiding contact. The "we're early" hypothesis is simpler. It requires only one assumption: we're early. Occam's razor favors simpler explanations. Fourth problem, maybe the future isn't as long as we think. The "we're early" argument assumes the universe will keep producing habitable planets for trillions of years. But what if something changes? What if dark energy tears the universe apart? What if some cosmic catastrophe sterilizes everything? What if the conditions for life are temporary? This is speculative, but it's worth considering. We don't know the long-term future of the cosmos with certainty. So there are legitimate criticisms of the "we're early" hypothesis. It's not proven. It's a hypothesis, a possibility, one explanation among many. But I think it's the most elegant explanation, and it's consistent with what we know about physics, chemistry, and biology, and it explains the silence without requiring aliens to be hiding, dead, or malevolent. It just requires patience. Others are coming. They're just not here yet. Okay, let's say the "we're early" hypothesis is true. What does that actually mean? How should it change how we think about ourselves and our place in the universe? First, it means we might be incredibly important. If we're among the first intelligent civilizations, we might be the ancestors of all intelligent life that ever spreads across the cosmos. Our decisions, our values, our actions might shape the entire future of life in the universe. That's a heavy thought. We could be the seed, the original template, the species that all future civilizations trace their lineage back to, whether directly or indirectly. Or we could blow it. We could destroy ourselves before we spread. And if we're among the first, there might not be anyone else to pick up the torch. The universe might stay empty. All that potential wasted. No pressure, right? Second, it means the silence is temporary. The loneliness we feel when we look at the stars, it's not permanent. Others are coming. Not in our lifetime, probably. Not in 1,000 lifetimes. But eventually. Imagine being the first person awake at a party. You're standing in an empty room, music playing, wondering if you got the time wrong. But you didn't. Others are coming. You just got there early. That's us. We're the first ones awake, and someday the room will be full of civilizations we can't even imagine, minds we can't comprehend, cultures so diverse and strange they'll make humanity look like a single note in an infinite symphony. We won't be there to see it, but it's coming. Third, it changes the meaning of the search for extraterrestrial intelligence. If we're early, then SETI might be looking for something that doesn't exist yet. We might listen to the cosmos for centuries and hear nothing. Not because life is impossible, but because we're the first ones broadcasting. Maybe instead of listening, we should be thinking about how to leave messages for those who come after. How to preserve our knowledge, our culture, our existence across millions of years. How to say hello to civilizations that won't exist for another billion years. That's a different kind of project. Not searching for others, but preparing for others. Building a welcome sign that will last longer than our species. Fourth, it gives meaning to our cosmic loneliness. Right now, looking up at the night sky, you might feel small, insignificant, lost in an uncaring void. That's a common feeling, and it's valid. But if we're early, our loneliness has a different flavor. We're not alone because the universe rejected us. We're not alone because life is impossible. We're alone because we're pioneers. First through the door, early to the party. There's dignity in that. There's meaning. We're not lost, we're first. Let's pause for a moment. Take a breath. We've been talking about billion-year timescales. Hundreds of billions of stars, the birth and death of generations of suns, the slow accumulation of heavy elements across cosmic history, the patient, grinding work of evolution over billions of years. And here you are, listening to this, a collection of atoms that somehow learn to think about where atoms come from, a pattern of matter that asks questions about the nature of patterns. You exist at a very specific moment in cosmic history, a moment when the universe is old enough to have created the ingredients for life, but young enough that life is still rare. A moment of transition, a moment of beginning. You were made of stellar ash. Your atoms were forged in the hearts of stars that died before Earth existed. You are the universe looking at itself asking, where is everyone? And the answer might be, they're coming. We're just early. That's beautiful. That's terrifying. That's the situation we're in. All right, friends, it's getting late, even later than when we started. Let me try to sum up what we've talked about. The Fermi paradox asks why the universe appears empty of intelligent life despite the vast number of potential habitats and the enormous amount of time available. One possible answer, we're early. The universe hasn't had enough time to produce many civilizations yet. The conditions for life only became possible relatively recently in cosmic history. Biology takes billions of years to produce intelligence. We're among the first to make it through. This hypothesis is consistent with physics, chemistry, and biology. It explains the silence without requiring aliens to be hiding, dead, or hostile. It just requires us to accept that we're living at the beginning of the story, not the middle or the end. If this is true, we have a unique responsibility. We might be the ancestors of everything that comes after. Our survival, our growth, our expansion into the cosmos might determine whether intelligent life flourishes across the universe or remains forever rare. No pressure, but also, there's hope in this. The silence isn't permanent. Others are coming. The universe will wake up slowly, over billions of years, and we get to be part of that awakening. Maybe the first part. That's something worth contemplating on a quiet night under the stars. This has been Stardrift FM. Thanks for spending this time with me. I hope you found something valuable in these thoughts, something to carry with you as you drift off to sleep or continue with whatever you're doing. Look up sometimes at the silent stars, and remember, the silence might not be absence. It might just be patience, the universe waiting for itself to wake up. And we're the first eyes to open. Good night, friends. Keep drifting.